Welcome to Earthly Teachings, where learning is clear and powerful. Today, we are working on Mathematics N6. Let's learn together. In this video, we'll tackle two important problems in differential equations. First, we will find the particular solution of a first-order linear differential equation, which involves using an integrating factor and initial conditions. Second, we will determine the general solution for a second-order linear non-homogeneous differential equation using the method of undetermined coefficients. By the end of this video, you will be able to solve these types of problems confidently. Let's begin with our first problem, question 4.1. The question asks us to find a particular solution. This means we'll first find the general solution and then use the given initial condition to find the constant of integration. The initial condition is y of pi over 3 equals 2. We'll set this aside for now and use it at the end. Looking at the equation, we can see its structure resembles a specific type of differential equation. This is a first-order linear differential equation. Its standard form is di y x plus a function of x times y equals another function of x. So our first step is to rearrange our equation into this standard form. Let's divide every term in our original equation by x. This gives us di dx minus 2 over x times y equals x squared times the secant of x times the tangent of x. This is the standard form we need. By comparing this to the standard form, we can identify that px is negative 2 over x, and qx is x squared secant x tangent x. Our goal is now to solve this equation. Now that we have the equation in standard form, the next step is to find something called the integrating factor. The integrating factor, or IF, is a function that makes solving the differential equation much simpler. It's calculated using this formula, which you should memorize. The formula is e to the power of the integral of p with respect to x. Let's apply this to our problem. We've identified px as negative 2 over x. So, our integrating factor is e to the power of the integral of negative 2 over x. We can pull the constant negative 2 out of the integral, leaving us with negative 2 times the integral of 1 over x. The integral of 1 over x is the natural logarithm of x. Remember, we don't need to add the constant of integration c here, as it would just become another constant later. So, we have e to the power of negative 2 in x. Now we use a property of logarithms to simplify this expression. The property states that a times the natural log of x is equal to the natural log of x to the power of a. Applying this, we get the integrating factor equals e to the power of the natural log of x to the negative 2. Another crucial property states that e to the power of len of a function is simply that function itself. Therefore, e to the power of len of x to the negative 2 simplifies to just x to the negative 2, and x to the negative 2 is the same as 1 over x squared. This is our integrating factor. The purpose of this step is to transform our differential equation into a form that's easy to integrate. Let's recap. First, standard form. Second, calculate the integrating factor. We've found our integrating factor. The next step is to use it to solve the equation. The solution for a linear first-order differential equation has this specific form. It's y times the integrating factor equals the integral of the integrating factor times qs with respect to x plus the constant of integration. Let's substitute our values into this formula. We have I times our integrating factor, 1 over x squared, equals the integral of 1 over x squared times q equals x, which is x squared secant x tangent x plus c. Now, observe the integral on the right-hand side. There's a wonderful simplification. The x squared in the numerator and the x squared in the denominator cancel each other out. This is a common and intended simplification when using integrating factors. This leaves us with a much simpler integral to solve. We need to find the integral of secant x tangent x. If you recall your differentiation rules, the derivative of secant x is exactly secant x tangent x. Therefore, the integral of secant x tangent x is simply secant x. Substituting this back into our solution form, we get y over x squared equals secant x plus c. This is our general solution. It's a formula that represents all possible solutions to the differential equation. We're almost there. We have the general solution, but the question asked for a particular solution. This means we must find the exact value of the constant c. To do this, we'll use the initial condition that was given at the beginning. The condition states that when x equals pi over 3, y is equal to 2. Let's substitute these values into our general solution. We replace e with 2 and x with pi over 3. So we have 2 divided by pi over 3 squared equals second of pi over 3 plus c. Let's break this down. First, pi over 3 squared is pi squared over 9. So the left side becomes 2 divided by pi squared over 9, which simplifies to 18 over pi squared. For the right side, secant of pi over 3. Remember, secant is the reciprocal of cosine. Cosine of pi over 3, or 60 degrees, is 1/2. Therefore, secant of pi over 3 is the reciprocal of 1/2, which is 2. Now we substitute these values back into our equation. We have 18 over pi squared equals 2 plus c. To solve for c, we simply subtract 2 from both sides. c equals 18 over pi squared minus 2. Calculating this value gives us approximately negative 0.176. The memo provides the exact same value. Finally, we substitute this value of c back into our general solution to get the particular solution. The particular solution is y over x squared equals secant x minus 0.176. This is the final answer. We have successfully found the specific solution that meets the given condition. Now let's move on to question 4.2. This problem involves a different type of differential equation. The equation is 1/2 times the second derivative of y with respect to x, plus the first derivative of y plus y equals 2x squared plus 5x plus 1. This is a second-order, linear, non-homogeneous differential equation. It's second order because the highest derivative is a second derivative. It's linear because the derivatives of y and y itself are not squared or in a function. And it's non-homogeneous because the right-hand side is not 0. Before we start solving, let's simplify the equation by getting rid of the fraction. Multiplying the entire equation by 2 gives us the second derivative, plus 2 times the first derivative, plus 2e equals 4x squared plus 10x plus 2. This is easier to work with. The solution to a non-homogeneous equation has 2 main parts. The general solution, which we call y, is the sum of the complementary solution, or yc, and the particular solution, yp. We'll solve for each of these parts separately and then add them together to get our final answer. Let's begin by finding the complementary solution, ic. This involves solving the associated homogeneous equation. To find the complementary solution, we ignore the right-hand side of our equation for a moment and solve the homogeneous version. The second derivative plus 2 times the first derivative plus 2i equals 0. The method for solving this type of equation is to first find the characteristic equation. The characteristic equation is a simple algebraic equation that we get by replacing the second derivative with m squared, the first derivative with m, and y with 1. Now we need to solve this quadratic equation for m. It doesn't look like it factors easily, so we'll use the quadratic formula. Remember the quadratic formula. For a quadratic equation x squared plus bx plus c equals 0, the solution is x equals negative b plus or minus the square root of b squared minus 4s, all divided by 2. In our equation, a is 1, b is 2, and c is 2. Let's plug these values into the formula. This simplifies to m equals negative 2 plus or minus the square root of negative 4, all over 2. The key here is the square root of a negative number. The square root of negative 4 is 2i, where I is the imaginary unit. Substituting this, we have m equals negative 2 plus or minus 2i divided by 2. Dividing both terms by 2, we get our roots. M equals negative 1 plus or minus I. Since our roots are complex, the form of the complementary solution is a special one that you should commit to memory. For complex roots of the form alpha plus or minus beta I, the complementary solution is yc equals e to the alpha x times the quantity a cosine beta x plus b sine beta x. In our case, alpha is 1 and beta is 1. Plugging in our alpha and beta, the complementary solution is ycc equals e to the negative x times the quantity a cosine x plus b sine x. The constants a and b are arbitrary constants of integration. Great. We have yc. Now we need to find the particular solution, ypp. This is the part of the solution that responds directly to the non-homogeneous right-hand side. Let's remind ourselves of our differential equation. The right-hand side, gi, is a polynomial, 4x squared plus 10x plus 2. For this method of undetermined coefficients, we make an educated guess about the form of yp based on g. Since g is a quadratic polynomial, our guess for the particular solution, yp, will be a general quadratic polynomial, x squared plus bx plus c. The memo uses different letters, C, D, and E, but the principle is identical. For this guess to be a solution, it must satisfy the differential equation. So we need to find its derivatives. The first derivative of yp is 2ax plus b. The second derivative of yp is simply 2a. Now we substitute these expressions back into our differential equation. We replace y double prime with 2a, y prime with 2ax plus b, and y with x2 plus bx plus c. All of this must equal the right-hand side, 4i2 plus 10x plus 2. Let's expand the left side of this equation. After distributing the terms, we get 2a plus 4ax plus 2b plus 2ax squared plus 2bx plus 2c, and this still equals the right side. We've substituted our guesses and expanded. The next step is to equate the coefficients of the powers of x on both sides of the equation. Here is our expanded equation. Let's start with the highest power, x squared. On the left side, the only term with x squared is 2a. On the right side, it's 4. Therefore, 2a must equal 4. Equating the x squared coefficients, we get 2a equals 4, which immediately tells us that a must be 2. This is our first unknown solved. Next, let's look at the x coefficients. On the left, the x term is 4a plus 2b. On the right, it's 10. So we set up the equation 4a plus 2b equals 10. We already know a is 2, so we substitute that in. 4 times 2 is 8. Subtracting 8 from both sides gives 2b equals 2, which means b is 1. We've found our second unknown. Finally, we equate the constant terms. On the left, the constant term is to 2a plus 2b plus 2c. On the right, it's 2. So 2a plus 2b plus 2c equals 2. We can simplify this by dividing everything by 2, which gives a plus b plus c equals 1. Substituting our values a at 2 and b at 1, we get 3 plus c equals 1, which means c is negative 2, and we have our final unknown. We have found a, b, and c. Now we can write down our particular solution. Yapi. Yapupua equals x squared plus bx plus c, so it's 2x squared plus x minus 2. Notice the coefficients are identical to those in the marking guideline, which uses C, D, E for A, B, C. We've done all the hard work. We found both the complementary solution and the particular solution. We found the complementary solution, YOC, by solving the homogeneous equation, which was e to the negative x times, a cosine x plus b sine x. And we found the particular solution, y plus p, by guessing a polynomial and matching coefficients, which is 2x squared plus x minus 2. The final step is to combine them to get the general solution. The general solution is the sum of these two parts, y equals e to the negative x times, a cosine x plus b sine x, plus 2x squared plus x minus 2. This formula contains two arbitrary constants, a and b. If an initial condition were given for this problem, we could solve for them just like we did in 4.1. Let's do a quick memory recap for this method. First, find yc by solving the homogeneous equation. Then find yip using the method of undetermined coefficients. Finally, add them together. This structured approach helps prevent mistakes. Let's briefly compare our solution to the provided memo. The memo gives the exact same complementary solution, e to the negative x, a cos x plus b sin x. And it also gives the same particular solution, 2x squared plus x minus 2, so our answer matches perfectly. Let's quickly summarize what we accomplished in this video. We started with a first-order linear differential equation and found its particular solution by calculating an integrating factor and using an initial condition. Then, we solved a second-order non-homogeneous equation by finding both the complementary and particular solutions and adding them together. This method of breaking down complex problems into manageable steps is a powerful strategy for exam success. Don't rush. Be methodical and check your work at each stage. Thank you for watching. Like, subscribe, and continue learning with Earthly Teachings. Let's keep exploring the fascinating world of Mathematics N6 together.